everybody. Thanks for attending this talk, named From Pits to Pods, the life cycle of an eBPF auto-instrumented application. My name is Macias, and I'm a staff software engineer in Grafana Labs. So what's this talk about? We will do a walkthrough in the internals of Grafana Beyla, which is a software component we use for auto-instrumenting applications and networks. It won't be a feature-based walkthrough, but an internals walkthrough. This will be a nerd session about the internals of the Linux kernel and Kubernetes, but we will also do an introduction of application observability and eBPF technology. When we talk about auto-instrumentation, what do we mean? Usually, if you want to instrument your application to monitor it and provide observability capabilities, I mean metrics, traces, sending logs to your observability collector or backend, usually between the application and its runtime, you need to insert an agent that will listen for the interactions between your application and the runtime or libraries in order to inspect what's going on and take data. For example, when your application performs an HTTP connection or opens a service that is called, this agent will listen for the connections, will inspect what's inside, and provide metrics and traces about the status of your application. This is the traditional way of instrumenting applications, but this approach is okay. I mean, if you can do that, just configure your application with an agent and send the data. You don't need other means of auto-instrumentation. But this has some limitations, or this doesn't work always. For example, we found people having a runtime that is too old. We have users still using a very old version of Ruby or even Python 2.7 that the modern observability agents don't support those runtimes. Or even if the instrumentation of that runtime adds a lot of overhead. For example, in Python applications, the instrumentation agent is written in Python, and the instrumentation agent is written in Python and is too slow. It adds a lot of overhead. Or even if the application is a compiled binary that doesn't directly interact with any runtime, just all the libraries are bundled in the binary. Or just if you don't want to touch your code, I mean, my code is legacy, I don't want to touch it, or I just want instant visibility of what's going on my system, because configuring your application to add agents, redeploy it takes some time. If you have hundreds of applications, maybe you just want, before you instrument it properly with a software agent or runtime agents, you just want to get some basic visibility. So here is where it comes Grafana Beyla with the approach of native eBPF auto-instrumentation. We'll enter in detail later about what this eBPF, but basically you deploy Grafana Beyla into your system as a regular process, operating system process, and this uses a technology named eBPF that allows you to inspecting your application at different layers, from the Linux kernel to the runtime and libraries. So injecting Grafana Beyla will insert some hooks into your system to try to get information about what's going on there. So this eBP, what I don't know if you are familiar with this term. It has gained a lot of hype in the last year in the Linux community, but it's not still well known by many people. eBPF used to mean Extended Berkeley Packet Filter. But it doesn't mean anything anymore, that acronym. Now eBPF just means eBPF. And it's a virtual machine that is built inside the Linux kernel. It's not a virtual machine in the sense of .NET or Java is in the Linux kernel, and allows you to insert hooks, some programs into your kernel functions and user space programs that will be triggered upon some functions invocations, for example. It's a very low-level approach. It's not like Java, for example, in which you have things like reflection, API, and so on. It's a very low-level approach. It's the eBPF programs are usually written in C and compiled to a binary format of this virtual machine, and needs to know how the memory is organized. So if you want to inspect a function call from eBPF, you need to know, for example, how the function call arguments are passed, how the different structures are rely in the memory in order to, at a binary level, know where to pick up the data. For example, imagine we want to track a TCP connection of a new TCP connection from your application. When you're in Linux, when your application wants to start a connection, invokes a function that is in the kernel named sysconnect. And then this sysconnect will establish the connection, will return a handler. If we want to instrument that with eBPF, we need to create two programs. One is a small program, usually written in C, but it can also be written in Rust, and compile it to this BPF binary. And on the other side, you need to monitor, to create a monitor program, which is the program that will actually listen for the data that is provided from this probe. Then your two programs will be deployed at two levels. First, your monitor program, in this case it will be Grafana Beyla, runs at the user space as if it was any other regular program with some special privileges to do some system calls. And this program is deployed inside the Linux kernel, and the Linux kernel will execute it every time the sysconnect function is called. So this BPF program, knowing if this sysconnect function is a standard C function, so you know how it is organized. You know that it returns an integer, it receives a file descriptor, and it receives a well-known struct. So knowing that and how C programs organize that memory, your BPF programs will pick up some information you might want to know. For example, from the SOC address, the destination IP or the destination port. Even you can retrieve the status of the result of the connection. And this BPF probe will put this information you want to know inside a eBPF map. And eBPF, a part of the virtual machine, it provides some data structures that are also internal to the kernel. And then there, the BPF probes can store information. This stored information will be read, can be read also by the monitor program at runtime. So this monitor program will know everything about this connection, the status of this connection. So the observed behavior will be that if your application is imagine is a web server and it receives an HTTP request, a GET request in the user's path, From eBPF, you can hook your application at different, or you can hook different applications at different layers in order to produce a metric or a trace with the information of that request. For example, it could provide a metric named HTTP request duration, and you will know that for that path, for the path users, the method get, it takes 200 milliseconds. This data will be reported into your system. The good part, the special part here is that this data is not reported by your application or by any library in your application, but from an external application that is able to listen or to peep what's going on your application or the kernel. Usually this kind of metrics and traces for HTTP, Beyla supports HTTP, gRPC, SQL, Kafka. This is not achieved as a single probe. You need to insert multiple probes and at different layers of your system, and then join all the information that comes from those probes. So the eBPF supports different types of programs that needs to be injected at different layers of your system. At the lower layers of your network stack, I mean IP, TCP, you have programs, BPF programs that can be injected in the traffic control or express data path. This is a Linux component that allows you to listen at the packet level. And with that, you can provide generic information about your internet connections. But then if you need, like, for example, IPs, ports, how many packets, how many bytes, which network interfaces are being used. But if you need application level data, like, for example, which HTTP methods, how long they take, each invocations, you need to start injecting in programs at the upper layers. The next layer are the K-probes. The K-probes are programs that Linux allows injecting into the kernel itself. So you can listen for some kernel syscalls, like this TCP connection we saw previously. There you can see host names, IPs. You can even get information about the connection status. You can know when a connection starts, when a connection ends. But if you want more high-level information, you need to use uprobes. Uprobes are programs that BPF allows injecting, not into the kernel, but into the applications it runs. So even if the application is not prepared for any kind of eBPF, or your application doesn't know anything about eBPF, Linux is able to execute programs when, for example, a given symbol of your application or a given function is invoked. And there you can start listening for example, getting higher level knowledge of your application, like which protocols are being used, HTTP, REST, protocol buffers, or even getting information about your payloads with methods or calls, SQL sentences, and so on. This might look super magic, like wow, I can listen to everything. But remember what I told previously, that any probe you insert requires that you know how the information is internally structured. For example, that means that, for example, investigating the internals of a Java application is almost impossible, because it will require you know how the Java bytecode is organized in memory, how the arguments are passed in the stack, whether it has been compiled to native code or it is still interpreting. It's very difficult. So, for example, Beyla is able to instrument Java or .NET applications, but it instruments it at this level, at the K-probes level, because even at the point, Java applications for connections or for sending data do kernel calls in order to establish the connection and send the data over the wire. So we can inspect data, Java applications from using a black box approach. So we know how they communicate with the Linux kernel, but we cannot know how it internally works. So eBPF is not magic. It has gained a lot of hype, but this is not the definitive silver bullet for all your problems. It has a lot of pros and cons. The pros is that it is pretty fast, even if the programs are compiled to a bytecode. Then the Linux kernel compiles it to native code just in time. So it is usually pretty fast and has a very, very low footprint on your software. Also, it is safe. The term kprobes or uprobes is not exclusive of eBPF. Before, the Linux kernel allowed you to load this kind of programs. But if that program crashes, your kernel will crash. eBPF has a pre-verifier, so it makes sure that it cannot load any program that is not guaranteed to finish or to not have. If the verifier cannot guarantee that, for example, the program doesn't have dangling pointers or doesn't finish, it will fail and you won't be able to load your programs. And theoretically, it has visibility of all your system, but as we said before, you have visibility to a lot of bytes. You need to know what those bytes mean. The cons: it is hard to debug and write. It works at the kernel level. So basically, debugging eBPF is via print and printing data in a queue that is provided by the kernel. And yeah, it's like watching the matrix. You just see a lot of symbols, and if you understand them, well. It is also dependent on the implementation details of the instrumented object. For example, an anecdote, we use it. It is pretty useful or many people use it to instrument Go applications, which are already binary, and it's difficult to dynamically inject any agent. But it has happened sometimes that a given Go library or even the Go runtime or the Go compiler has changed some implementation details. For example, how the arguments are passed to a function, and upgrading your application to a new version of Go broke your instrumentation until we implemented it in a newer version of Beyla. And also another cons it has is that it requires elevated permissions. So you cannot inject anything in your kernel that gets full visibility of your kernel without providing some permissions, at least to load those programs. So as we said before, we can provide, or Beyla provides, metrics and traces at different layers. At the L3 and L4, I mean the network and connection layers, you can get basic information about your connections, basically connection status, how many bytes are going through different endpoints in your system. But it has an advantage. It is just these kind of programs are inspecting very stable APIs. The TCP/IP stack has been the same for the last 40 years, maybe, with small additions, of course. So it's very unlikely to break your information, but or to break your instrumentation, but the information it can provide is very limited. And then we can provide also application-level metrics, which provide more information about your actual applications, not just your internet connections. Like in HTTP or gRPC, you can know which methods are invoked, their response code, request times, and we support other protocols like Kafka, Redis, SQL. The problem is that sometimes some user comes saying, do you support this new library, in asynchronous library from Go? No, we support some previous libraries, so when a new implementation comes up, we need to explicitly implement it, because every library, every runtime has different functions, different arguments, even they have different ways of handling asynchronous, because nowadays most web frameworks are asynchronous. So when we need to get information from all the requests, but we also need to relate all the information we get to a given or to the same request, because currently multiple requests might be handled at the same time. So we need to group our information. So the problem is that we can break things from time to time when you using this kind of metrics. It is important. This is very low level. We're talking about basically here we are relying at the process level or kernel level of our programs, but most of our users, Beyla can work with standalone as a standalone process, but I will say 95% of our users are Kubernetes users, and we want to provide them also with a good solution for Kubernetes. In case you are not familiarized with Kubernetes, in Kubernetes your applications are executed as containers that run inside pods. A pod is just a unit of execution in Kubernetes in which you can run different containers, and those pods can be organized at a higher level, with higher level semantic structures like deployments, replica sets, daemon set, services. And all of them have their name, their namespaces, their metadata. The problem is that with Beyla, being a regular host process running or listening to the kernel stuff, basically Beyla directly sees everything running in your Kubernetes node. It sees it as a bunch of processes, and each process, what can we know about a process? The command name, which is often Python or Java, the process ID, which is a number, or even the host name of that node. But our users actually need something more rich. Kubernetes users need more information. They don't really care about the PID or the command name. They might have 100 different Java services, and the command name will be reported as Java for all of them, so that information will let them discriminate data by service. They want to know what pod it's a failing program running on, under what deployment or daemon set or stateful set name, or what service they belong to. Even the namespace are very important in Kubernetes, because you might have a service name or the same service name spread about different namespaces. So we need to know, and this is what is given the title to this talk, how can we go from the PID to the pod information? So this is our journey from a PID to a pod. Now we are starting to see some internal implementation details of Beyla. Beyla is able to get the information or the metadata from different sources. For example, from the eBPF probes, we can get the application level runtime metrics. This is how your application is behaving. From the proc file system, I don't know if you are familiarized with Linux, but there is a folder in the system /proc where you get almost all the information of your running processes, like the PID, the commands, the status, but even also other lower level information we'll see later. And also Beyla can connect to the Kube API. Each Kubernetes pod, when it runs in Beyla, in that case, will run as a regular Kubernetes pod with some extra privileges. Each Kubernetes pod can get permissions to access the Kubernetes API. The Kubernetes API allows you managing your Kubernetes cluster, but it also allows getting a snapshot of your whole cluster, all the pods running in your cluster, with some extra information or the metadata of those pods and services and deployments. But there is no direct mapping between a given host or a given pod and the PID it belongs to, or the process ID. Also, there is an added extra difficulty. This is playing in God mode. I think this comes from an old video game named Doom. The most difficult level was God mode, because Beyla, a process, PID, will be different depending where do you observe it from. If you are, imagine we have a process that runs in a pod, and that process might have a PID different depending where do you listen it from. If you are running a program at the node, at the host node, you can get it. You can get a number. But if you enter in the if you go to the container runtime that runs the containers of your Beyla cluster, it will have another. But even if you go inside that pod and you observe it, you will get another PID, usually PID 1. And we need to be aware of those differences because Beyla can be deployed at different point. For example, the eBPF probes will see the PID as seen by the kernel. When Beyla is deployed, as Daemon said, this is Beyla is deployed as a pod in a node, you will see the second PID. And even Beyla can be deployed as a sidecar. This is a container inside your pod to observe only that application. It will get another PID. So we need to maintain a map with all the PIDs. How do we know that PID 1245 belongs to this container runtime and it's not another PID going of another process running in the kernel? Probably in the kernel there is another PID 1245 that is not this, but is another problem, another process. This is because PIDs have namespaces in Linux. So it's not the same, the PID 1245 from namespace X than the PID 1245 running in the namespace 1, which is usually the lowest level namespace. So we need to be aware of those stuff. So fortunately, from the PID, from the process information in the proc file system, we can know the container ID. We can extract there the data about the identifier of the container that runs that process. Imagine the process that is being instrumented, because Beyla can instrument multiple processes in your host. We can extract the container ID. And from the Kube metadata, we also are able to get the container ID. So matching the data from different sources and building your internal database will allow to getting the PID or to match a PID, a running process, with the pod. So this is got from the userspace process discovery, and this is from the Kubernetes API. A feature of the Kubernetes API is named Informers, which is just a subscription-based API to get any new update on your system. But also, when we have our processes, our pods, but when the eBPF probes, your instrumented application, gets a service call, for example, it is triggered an application span. And this application span has a PID, it has many information like protocol, the client server, the method, the bundle size, and it has a PID namespace, but as we said, this PID namespace can be pretty different depending on where is or whether you get the information from the eBPF probe or you get this information from the from Beyla, depending on the deployment mode. So we need to go to the Linux kernel functions. So this is the nerdiest slide in the presentation. Basically, eBPF has some extra information like getting the current PID and group ID of the program that has been cached from a probe, and it returns this task struct. This get current task returns this task struct in which you get a complete map of all your PIDs and all the namespaces for that given process. So in that case, we by convention go always to the outmost namespace and get there. The outmost namespace is actually the lowest level namespace, the host namespace, and then we match the information there with the PID namespace of that pod. Here we have, for example, for each namespace we have which PID gets or which PID is this process visible under all the namespaces. So we need to go very, very, very deep at the process scheduling layer to be able to identify what process our tasks belong to. So the journey of an application trace basically is from the eBPF probes, you get some low-level information like PIDs, prototypes, internal eBPF or internal request information. Then you have a Kubernetes data decorator, which from this host PID, user PIDs, use as key, you have an internal database matching all these PIDs to your Kubernetes information, so you can decorate it with something that is more meaningful for more users, like the server host name, pod names, etc. And then you can provide metrics and traces. This is a short demo how this will work. In Kubernetes, we have this is a copy. Here is a backend service. How to instrument it in Kubernetes. First, this is the minimal. Of course, there are many other configuration options, but this is the minimal Beyla configuration. You need to provide a way to tell Beyla which applications you want to instrument. You can select your instrumentation, your applications by port, by command name, or whatever. But you can also select your applications by Kubernetes. In that case, we are telling Beyla to instrument all the pods in the demo namespace and all the pods in the block namespace. If this accepts a regular expression, if you just set there a dot, it will instrument everything into your system. And also, okay, this is some other information that is optional. Also, you need to tell Beyla how to export your information. Beyla, I forgot to mention that Beyla exports the data in OpenTelemetry format. So OpenTelemetry format is not a Grafana exclusive format. It's an specification driven by the community, by an open community. So it's an open specification. You don't need to use Grafana to use Beyla. You can use Beyla with any other competitor that enables OpenTelemetry. But you need to provide a way of exporting the information. Those are the standard OpenTelemetry endpoint and headers, environment variables for enabling a connection to an OTLP endpoint. And basically, once you instrument your application, you get your metrics. Here is a open dashboard we provide with all your information about your metrics of your web services. And this is also a feature of Grafana Cloud that allows you to navigating your system, getting the metrics, and even we can get the traces. Not only the metrics, but we can get traces and distributed traces. We can know which services call other services, how long they take, and so on. And you can provide, also you can get a service map. Grafana is very committed with the open source community. This Beyla product is still open source and will be open source forever, but we have donated it to the OpenTelemetry Foundation under a different name. So Grafana Beyla will continue existing, but the upstream version will be available under the OpenTelemetry eBPF instrumentation project. There, we are doing a upstream first development. So every new feature we add to Beyla will be first available in this repository, and then we will incorporate it in Beyla. Beyla will keep existing and will keep being open source but it will be more focused to a Grafana supported distribution, and will also add extra features that might be useful for its integration within Grafana and Grafana Cloud. But this version will have 90–95% of the features of Beyla, but supported and backed by a community. So thank you a lot for your attention. If you want to keep in touch with us, you have two means: Grafana Beyla, the Grafana Beyla GitHub, and the Beyla channel in our public Slack. And if you prefer to interact with the community, which is formed by many other contributors that are joining this effort, you have the OpenTelemetry GitHub and the OTel eBPF instrumentation channel in the cloud native Slack. Oh, I forgot to mention you at the beginning of the talk that you can, in the program of this conference, you can get a link for evaluating this talk. So any question? Yeah? Yeah, good question. You have two ways to do that. In Beyla, you can select which concrete metrics and which attributes you want to report, and you can even filter by attribute. But it is so you will decrease the number of metrics and traces. But also the other option, this is a very basic setup. If you connect Beyla instead to send directly data to Grafana Cloud, if you have an intermediate collector, the OTel collector or Grafana Alloy, you can add there extra filtering options or consolidation options to decrease the volume of data you send to Grafana. Someone else?
Great talk, Mario. That was really interesting. So, by the way, so my company and we tried to instrument OpenTelemetry last year for a couple of SDKs, Node.js and PHP. So at that time, Beyla wasn't fully donated to OpenTelemetry. Right now it is. We wanted to know, like right now with this donation, if we can auto-instrument this, for example, SDKs. What's your opinion? Thank you.
Yes, you can currently instrument that. The donation, the code here in the donation, it is still not marked as stable, but and secret, I tell you, is that we use it directly into the stable versions of Beyla, so it's somewhat stable. The problem is that you won't find any, this has been very recently been donated, like 2 months ago, and we still haven't provided any documentation. So you will probably need to navigate the Beyla documentation or directly joining this Slack channel. We are pretty responsive and try to help us as much as we can. But yeah, you should be able. You can find some pitfalls because the youngness of the process, like documentation. Okay, no more questions. Okay, thank you very much for your attention.